Okay, pass it up. One more. So just in the future, don't wait for me to say pass up the homework to put your heading on. Just have it ready and just pass it up at the beginning of class. Okay, so we were here with our creating the step function, and we had said let's define the step function only for x greater than or equal to a, because a is our starting value, and we're going to start accumulating from a based on this rate of change function. But then there was another issue that we had with the step function that appeared. What was the other issue? What's that? Yeah, so these lines, these vertical lines, right? Those shouldn't be part of our step function, right? So what is it the graphing calculator is doing that it's creating those lines, those vertical lines? How do you suppose the graphing calculator actually plots a graph or draws a curve? How does it draw a curve? Does it know every function in the world and it's just waiting for us to type in e cosine x so that I know that one, and it just graphs it, right? What does it do? What does graphing calculator do to create a curve?
A ton of tiny points.
What's that?
A ton of tiny points at each very small x value.
Okay, so then it would look like points though. So okay, that's kind of what it does. But what does it do from there? What?
Connects them.
All right, then it connects the dots, right? It's gonna find a bunch of ordered pairs close enough together so that our eye can't see that when it does what? It's gonna connect the dots, and then it creates the curve. So why are we getting the vertical lines? Why are we getting the vertical lines? Okay, so it comes to the end here, and then what does it do? Yeah, sure.
Is it because it's connecting the points?
Yeah, so it's plotting a bunch of points, but then it's connecting the dots, right? So there's a point at the very end of this step, and then the point at the beginning of this step, and it's going to connect all the dots. We don't want it to do that. So what we can do is we can tell it to graph this function step everywhere except at our breakpoints. If we say don't graph it at the breakpoint, then that should remove that line. So how do we define the breakpoints?
So the x from 1 point to the real step function breakpoints are included.
What's that?
In the real step function, aren't those points included? No, because that's not a function. Well, not the points in between, but the point.
Yeah, like he's saying if you're using left x, the left side is going to be included here, right?
We're getting rid of that.
What's that?
Are we just getting rid of the part in between?
Yeah, so our eyes won't be able to see the difference between having the endpoint and not having the endpoint. But then it'll get rid of that line, and so we're just creating an image, right? We know that the left end is the actual rate at the left end.
All right.
Yeah. So, but we want the image to mimic what we want. Okay, so where are the left endpoints? For all values of x. So we can say if, on the step function, we can say if aren't these right there? Aren't those the endpoints? Right? The floor function for any given value of x.
Yeah.
It's the floor out to the distance of x from a, number of intervals, chop it off. That's our left endpoint. So we want it so that when this is not equal to, so not equal is option equals just what's inside, because just what's inside is going to be all possible values of x, and then if we take the floor, we'll get the left side. Connor?
Do you know how to do the non-equals in Windows?
I don't. It should be pretty easy to figure out, though.
I tried like
Control Shift N as in Nancy?
Shift N.
As in Nancy? N as in Nancy? Control Shift N. Yeah. That's not what I wanted. Just want this. So do you see what this is doing? So this is like all x values anywhere, and we don't want them equal. We don't want to plot it when it's equal to what we get at the floor, which is going to be those left endpoints. So that gets us the image that we want. Okay, any questions on this? So it's getting harder, but so we're getting into this is where we've been heading for a long time. Getting into building, we want to build our accumulation function out of the rate function, and there's lots of pieces that are coming together here. You can't really forget any of those pieces. So it's getting more difficult. Lots of symbols, but we've taken our time to really understand what every symbol and expression means. Okay? So don't get under the mentality that once I have the formula, that's all I need and I can just plug into the formula. No, you have to keep understanding what all those expressions and symbols mean and the relationships. How we got that. It's not getting easier from here. It's going to continue to get harder. Okay? So your homework for Friday is a little bit longer, and so here's what I recommend. Don't try to sit down in 45 minutes on Thursday night and finish this. So because it's getting more difficult, and it's getting more involved, we have more pieces in play, do it in 2 or 3 or 4 sittings. So you sit down with it sometime today and start working on it, and you do what you can. And then you go to another class, or you go play racquetball, or you do the laundry, you have a meal, and then you sit down again. And then suddenly a few more things will start to make sense. Okay? Then tomorrow morning or tomorrow afternoon, you work at it again. And every time you work at it, it'll start making more and more sense. Things will start coming back to you. Okay? Watch today's video. Okay? Watch today's video. Then try it again. Okay? So if you do it in little chunks, you'll see progress. You'll see really good progress. But if you try to do it all at once at the last minute, you're just going to be overwhelmed and probably frustrated, and it won't work out. Okay? So that's my recommendation for working on homework from here on out. So let's start with a review. So we've done a lot, so we'll start with some review here. Unless anyone has a question. Yeah. What's that?
An A over a B inside of a bracket. How do you make that bracket again?
Are you just talking about parentheses?
Yeah.
A point, you mean?
No, I got it.
Okay. You meant a point. How do you make a point? How do you draw a point?
I meant I don't know what it's called. Bracket with the X.
Right, but what you're trying to do is create a point, an ordered pair of a point.
Yeah.
You mean this?
Yeah.
This is a point. So it's not just a bracket, it's a point. So yeah, Control 2. Okay. So let's... Here we go. So here's an illustration that should have lots of familiar elements in it. So and then I have this sum here, okay? So it's illustration and the sum. Get a partner. I'm going to give you a couple questions at a time. So get a partner and discuss this, and this is just to really make sure we got all the, we're reviewing everything we've done so far. So when we move on to the next step here, which is we're actually ready now to build our approximating accumulation function. This is huge. So we've been working on this for a month now. Okay? So before we do that, let's really make sure we got everything down from before. So get a partner, talk about these two questions, and we'll regroup in a second. Go. Everybody has someone they're talking to. If not, introduce yourself. Make a group of 3. Groups of 3 are fine too.
No, it says by the blue curve.
Where it crosses the middle, so see mid.
Yeah. Oh, the midpoint?
Okay, let's regroup. David. Blue curve. What's that? What's that? What's the blue curve? Okay, it's a rate. It's accumulation function. The blue curve is accumulation function. Let's see. Olivia, agree with that? The blue curve is the accumulation function.
I said the blue curve is something that's displaying the rate of change.
It's the rate of change function. Those are two very different things. So, which? Adelaide. Blue. Is it rate of change or is it accumulation? I think it's rate of change. It's rate of change, okay? If we're making a step function out of it, it's a rate of change function. The blue, is it the actual rate of change or is it an approximating rate of change? Actual rate of change. This is the starting point. We know how fast something is changing, and we want to know how much of it we have. So that blue curve is representing how fast, whatever our quantity is, how fast it's changing at any value of x. Okay? All right. So it's our actual rate of change function. Pink step graph. Andrew.
It's the approximation of the rates of change by making them constant over intervals.
He said the approximation of the rate of change by making them constant over intervals. What do you think? Agree with that? Well said. Well said. Okay? It's the approximation of the rate of change by making them constant rates over intervals. Exactly. Okay? And why do we want constant rates to approximate the actual rate function? Lauren, why do we, if we've got the actual rate function, why are we changing it to some estimating rate function with constant rates? What's the point of that?
That's so we can bring it up to being able to find the accumulation without having to add up every single thing.
Right. Yeah. Yeah, so it's in order for, so we can have some easy mathematics to get actual accumulation and what represents that kind of easy mathematics that we're going to do with those constant rates. Autumn.
Y equals K delta X.
Y equals K delta X. Close. Delta Y, right? Each is going to be change in Y. So from each of those we can get a change in Y just by taking the rate times the change in X. Right? That's our proportionality of changes. Constant rate of change. Constant rate of change. Okay, cool. So let's try these two. Okay, so question number 3. Name all the characteristics of the pink step graph that you can. That's what we've been working on. And then consider the third interval, which I'll highlight in a moment here, from 0.6 to 0.9. How is its constant value determined? And represent that value symbolically. Okay, go. So this is.
Oh, yeah, it takes whatever.
Solution to mid of x is when we put into R of x.
Okay, Dan, one characteristic of the pink step graph.
Showing a constant rate of change in the next.
What's that?
A constant rate of change within an x interval.
Okay, so we've got constant rates of change. So, Tyler, another characteristic of the pink step graph.
The rate of change does not vary or change within the x
Okay,
interval.
this particular step graph, characteristics of this particular one. Rohit. It's a mid. Made from the mid, okay? Mid-based, how about? All right, Beth, what else?
I don't know, that's what I was gonna say.
Okay, what is another characteristic? Yeah, Jacob. Delta x is 0.3. Good. Another characteristic. Yeah, DJ. A equals 0. Anything else? So another thing we can talk about is how many intervals are we showing? How many intervals? And so that's usually the value n is the number of intervals. How many we got? 10 intervals. Okay, cool. Anything else you want to mention about? Yeah.
Can we say that the output, does this even make sense? The output from R of x is the input for step of x?
The output of R is the input into, what is the input into step? What kind of thing is the input into step? Is it a rate? So what you're saying is it a rate? Is that a rate going into step? What is it? Yeah, so any x value goes into step. So you wouldn't put a rate into there. You wouldn't put...
Confused from yesterday.
Yeah, no, so what is the step function? Step is, so this is what we're going to... See, the step function, it is rates. These are the output of the R function and the output of step are both rates.
Okay.
They're both rates because step is an approximating rate of change function from R.
Step would just be a constant, and the other one would just be differing at every single point, right?
Well, it's different constants, right?
Right.
So for over here, when x is over here, it's this constant. When x is here, it's this constant, right? Okay, how can we, so in the third interval, how is this constant value right here determined? So where does it come from, that constant value? Nigel.
It comes from the
the function value at the midpoint, which is going to be 1.5 past 0.6, so the function value of 7.5.
Okay, he says it comes from
0.75.
He says it comes from the function value at the midpoint of the interval. Is that right? That was going to say. Okay, yeah, exactly. So it comes from. So how can we? What is that constant rate? How could we write it, Kaiser? How could we write what that constant rate is right there? How could we represent it?
Left of x plus x divided
Okay, left of x. So, but that value, is that a rate or is that an x value?
2. Right.
It's a rate. So which rate is it? How could we represent it? This, Lauren. Do you know how we could represent that rate?
Wouldn't it just be, I just don't know what to put into it, and I don't know.
Okay. Helios. R of left of x. Is it R of left of x? R of mid of x. But I want this particular rate. Lots of hands. Let's see. Who hasn't? Sharon. Yeah, this is R of 0.75. It's the true rate at the midpoint of the interval, right? So the whole constant rate for that whole interval is found by the actual rate at the midpoint. So R of 0.75. Does it make sense? So if you couldn't come up with that, so that should make sense. Every rate in the step function comes somehow from the original rate function. In this case, it's coming from the midpoints of the intervals, the rate at the midpoint of the interval. And so the midpoint of that interval is 0.75, so we plug it into R, we get that constant rate for interval 3. Okay, so how can we write the whole step function, step x, in a different way? Okay, take a moment and figure that out with your partner. How could we write step x? Where does it come from? Where does the whole function step x come from? Go.
So you have a full function, then you have that mid function. You have the mid function.
On this.
Well, you have to have the left.
Okay, some people are saying it. Some people said it before. Do you know what it is? Where does the step function come from?
I don't know.
That's honest. Okay, well, so if we had this point right here, what would we need to do first? Say we had this x value right here. First, that x value, whatever it is, we would need to find what? We would need to change that x into the mid, right, the value of x at the midpoint. And then plug it into the rate and get the rate at the midpoint. So what is it? R of mid of x. So what happens? Any x value that you pick, it will change that x value into the midpoint x value of that range and then give you the rate. So your initial x, the original x value now is assigned the rate at the midpoint. And that's what we want. We want every single x in that interval, first gets assigned to be the midpoint x value, and therefore every x in that interval gets assigned that rate. You see? It's all about functions. What goes into mid x? An x value. What comes out of mid x? Another x value. The x value at the midpoint. And so then we plug that x value and get that rate. So step of x is the same as r of mid of x. Okay, so now let's look at this sum. So first, let's break it down. So what is, say, one of these r values? What does delta x mean? What is the whole thing multiplied? And what is the whole sum? Okay, so 4 things. What does an r stand for? What is delta x? What is a product of those two? And 4 would be, what does the whole sum represent? Go. Okay. Judith. I'll give you the easy one. So what is, suppose what's R4? What is that?
So that would be the rate at the 4th interval.
Okay. Is it a constant rate or like a particular rate? Is it represent a constant rate over the interval or a particular rate?
I think it's particular.
It's constant.
Yeah, so it's the constant rate on interval 4. It's the constant rate on interval 4. Okay, what about delta x? Keep going.
So that's the interval at each specific point.
Okay, what about the interval is it? Delta x.
It's the value that corresponds to the y value, so it's like the rate over that interval.
Delta x is the rate over that interval. Tyler?
Isn't it just the length of the interval?
Yeah, so it's the width of the interval, right? So it's the width of the interval. It's not the interval, right? Delta x isn't the interval. It's the width of the interval. It's a number. It's a number, okay? What about the product, R2 delta x? Megan?
It's the rate at second
Mhm.
times the length, which would be delta y.
She says it's delta y. Say delta y2. What do we think? What does delta y2 represent? Daniel? What does that mean?
Change the y.
Okay. What's our goal? We're building what? Accumulation function. So what is delta y2 in that light?
Accumulation over the second.
To the
Isn't it how much y changes in that second interval?
Okay, so what does that have to do with accumulation?
When you add up all of them, that's the accumulation, is that it gives you how much it changed in that interval.
Yeah.
And the previous one gives you how much it changed in one, so if you add them up, you get the accumulation.
Right. Yeah. How do things accumulate? So each delta y that we're adding together is a little bit of accumulation. A little bit of accumulation. The change in y, the change in our quantity, right? This is the rate of change of that quantity. Y is measuring the quantity itself, and so each delta y is a little bit of change of that quantity. Okay, so then the whole sum we said is? Okay, summation. Okay, but in the context, what is the summation? What does that mean?
Total accumulation.
It'll be the total accumulation in these first 10 intervals. Total accumulation in these first 10 intervals. Okay, what about from 0 to 1.2? What shows the accumulation from 0 to 1.2? Dan?
The rate of each midpoint, okay, there's what, 4 intervals.
Okay.
The rate of each one of those midpoints added together.
You want to add the 4 rates together, is that right?
The change in watt or R, the rate times the mid x value. Or the rate add the mid x value times.
So how about related to this expression right here? What shows the accumulation from 0 to 1.2?
The first 4, R1.
That's fine. Just the first 4 added together, right? First 4 added together. So that would show the accumulation from 0 to 1.2. Okay? So we haven't done this in a while, so let's remember. How would we write that as summation notation? So we're going to do J for kicks here. All right, so J goes from 1 to 4. And then the whole point is, rather than writing this repeated thing over and over again, we can just write it once. We just write it once. And that's exactly the same as summing those 4 things together, right? Okay, so here's kind of where we're going next. What above shows the accumulation from 0 to 2.2? Go, talk about it. 0 to 2.2. So talk about that.
Is the middle after 2 2.5?
So that extra from 2.1 to 2.2, you need to add like another R times delta X times third.
Okay, Stanley, tell me.
Well, you would sum the first 7.
Okay, let's do that with summation notation. What would that be?
I.
Sure, we'll go back to I. That's great.
1 to 7.
7.
So then R sub I and delta X, and then you got like an extra third of an interval.
Okay.
So it'd be like plus R8 or sub 8 plus or times a third of delta X.
So what would it be?
Delta X divided by 3.1.
What do we think? Like what he did? Is that what you thought? So he added up the first 7, but that only takes us to 2.1. Well, now our x value landed in the middle. It landed in the middle of an interval. So we still have a little bit more accumulation to take care of. What's the rate now in that interval? What's the rate? What are we calling it? It's R8, right? So this is our R8 interval. Is it times delta x? No, only as far as we go. Only as far as we go, starting at the last endpoint here. And we go 0.1 to get to 2.2. So we don't do a full delta x. We have a partial interval that we're going to add on the delta y for that part of an interval. Okay, because if we just come along here and I just pick an x, very unlikely I'm going to land on an endpoint. Much more likely that the current value of x is going to be in between. If we want to evaluate that accumulation, we're going to need a bunch of full intervals plus a partial interval of delta y, right? Okay, so that's where we're going here. Okay, so we're building this accumulation function, and for now, this accumulation function is it approximate or exact? Approximate because it's based on the step function. The step function, not the actual, okay? So, represent a of 1.2. How do we represent a of 1.2? We said that's the first four added together, right? Because it's 1.2 takes us exactly to the end of the fourth interval. Okay, but the question is, what specifically are those rates? We can't, if we're going to do this, we're going to make a function out of the original rate function. What specifically are those rates? So each one is r of what? Okay? So this is for you. So figure out r of what? Each one, r1 is r of what? R2 is r of what? Etc. What are they? Figure them out.
Or is it r times something times delta x?
No, r is a function, right? It's a function. It's not times, right? Function notation. It's a rate at given different values of x. Function notation, right? Okay, so what is R1? What is R1? Oh, I'm sorry. So I switched it to left, right? Step got switched to left. We're going to work on left now. The previous example was mid, just to give us something different. Now this is left. So for left, what is R1? R of 0. Okay? R2? R of 0.3. The left side of each, so we're taking the rate at the left side of each interval. Okay. What about in terms of a and delta x? So no longer as numbers. So suppose it was for any starting value a and any delta x. What would the input into the rate function be to get these first four rates? Go. Got it?
It starts at A. So why is it the first one?
Yes. What is the
It starts at A.
So if we're using left sides, what would the first rate be? R of what? Katie, what would the first rate be? R of what? A0? What do you mean A0? Starting point. So what is our starting point? Richard, what do you think? Yeah, but now we want it in terms of A and delta x. Yeah, for this one it's 0, but we could start anywhere, right? We could start anywhere. And that's what we're saying now in terms of A and delta x. David? R of A. Agree with that? Yeah, be R of A. Okay, if we're using left sides, the first interval, the left side of the first interval will be our starting point. That'll be A. Okay, so now what would our R2 be? We need to go here, which is A plus delta x. And then for the third interval, R3, we're going to add 2. And now the patterns, once you got the pattern, you just write them down, right? Does this make sense? So the first rate, if we're doing left, the first rate will be determined by the rate at the starting point, and that'll be the first constant value for that first interval. And then we need the rate starting at delta x over to be the rate for the second interval. So we want to write this in summation notation. I'm using j, okay? So this is j equals 1 to 4. So how can we, in terms of j, write what the jth rate is? So j equals 1 is our first interval. So here are the j values. 1 is the first interval, 2 is the second, 3 is the third, etc. So j is the number of the interval. Okay? So what, in terms of j, what x value are we putting in to get the rate for the jth interval? So you can figure it out. Zoo, did you get it? A plus A plus j minus 1. That all goes in there. Agree with him? We always have the A, right? We always have the A. How many delta x's are we adding? So for the second interval, how many delta x's? 1. For the third interval, how many delta x's do we add? 2. So the number of delta x's that we add is always 1 less than the interval that we're in. That's it. Okay, did I lose anybody? It's all important. Gotta stay with me here. Yeah? Okay, so all of them are A plus some number of delta x's, right? So if this is the first interval, how many delta x's? 0, right? If this is the second interval, 1 delta x. Third interval, 2 delta x's. Fourth interval, 3 delta x's. So in the jth interval, there's 1 less delta x's than the interval that we're in, that we're adding to A. Are we good? Okay. That's only half the battle, though, because usually... So what about now 2.2? What's the general idea behind finding the accumulation to 2.2? What will the general idea be? The big picture. Connor. We want to accumulate up to 2.2 now. In general, what will that process look like?
2.2, you have a sum of the first 7 intervals.
Right.
Now be the R sub whatever.
Okay.
Over 7, starting at 1.
Okay.
And then you would add on to the end. A is equal to, I'm sorry, delta x equal to 0.32 is correct?
Yep.
So that'd be 1/3 used to 0.1 times delta x. I'm sorry. 0.1 times R sub A.
Yeah, so yeah, you're giving me more detail.
Add on 0.1 times R.
Yeah, so you,
Summation of the previous 7.
yeah, you got it. You're being very specific. I was just wanting, this is the idea. We got the first 7 full intervals, plus a little more, plus a little more. So it was great. It was great. You just more the detail than I wanted. But now we're going to the detail now. Okay. So first 7 intervals, full intervals, plus a little bit more, right?
Caught me off guard there.
Okay. And what is this? This little more is the accumulation from part of an interval. Okay. We already did the first 7. So what will it be? From 1 to 7. And we just did that, right? So it's going to be R of out to the left end of the interval times delta x. Okay? Now we got to get this a little bit more. So that little bit more is, we said R8 times 0.1, right? But we need that. So first of all, what is R8? Where's R8 coming from?
Where's the 3 and the 8 interval?
Okay? So we need to get all this stuff here in terms of our input, 2.2, right? If we're building a function, then this needs to, we need to be able to find that based on the input, based on 2.2. So R8 is just R of the left end, right? 2.1. And the little bit of the interval is the difference from where we're at to that left end of the interval. Okay? And what is R of 2.1? Well, that's our R of left of 2.2. So this is the rate at the left end of the current interval for that value of x. And then this is how much of that interval we're going to go. The final value minus the x value at the left end of what it is. Should make sense. So this is the rate at the left end of the current interval. And then how far we go. This is the partial delta x here. Are we good?
Why is it minus left of 2.2?
Okay, what is left of 2.2?
Oh, it's 2.1.
Yeah, it's the left end, right? So we need the rate at the left end, and then we need how far we go past the left end. Which is going to be final minus initial, right? So let's put it all together. What's that? A, starting point. What's that black bar represent? Yeah, so it's where we're accumulating to, okay? And we call that the current value of x. So we think of x increasing, right? And then we pause life and we say, okay, that's the current value of x, or the input, where we're accumulating to. What's that right there? Beth? I'm pointing right at that red point, though. So it'd be the left side of the interval. So this is left of x. This is the x value at the left end of the current interval. Okay, in general, what is a of x going to be? So in the big picture, how are we going to get what a of x is? Anybody? Autumn, in the big picture. Where's
How are we going to get what A of X
yeah, so
is?
what's the accumulation of this, whatever this rate, the quantity for this rate, up to there, what's that in the big picture, what's that going to look like to get that accumulation?
You're asking me like what function we would use?
No, I'm just building this accumulation function kind of has 2 pieces to it. What are the 2 pieces, Lauren? Okay. Okay. Dan, that's right. Yeah.
The sum of all those intervals intervals plus the little change on that last interval.
Right. So we'll always have a sum of full intervals, and then we're going to have a little bit more to get to our x value. Okay, so some bits changes of many full delta x intervals. Plus probably a little bit more for the last partial delta x interval.
But you also have to add before a the amount.
What does a mean? Right?
So it's kind of this a sub 1 plus like a sub 2 for the formula. If the change in x1 plus the change in x2.
No, these are all delta y's, right? These are we're adding up delta y's. A bunch of delta y's from full intervals, and then a little delta y from a partial interval. Okay? So we did this, right? So we said adding up those full intervals looked like that, and we came up with this formula for the full intervals. Question is, how many full intervals are there? So who remembers what we've done? How many full intervals out to, so if we start here at A and we end at X, how many full intervals are there between A and X?
X minus a divided by delta x.
One person's got it? Do you remember?
A minus x over interval x taken into the form.
Two people got it, right? This was our x minus a over delta x, the floor of it, right? X minus a over delta x gives us how many intervals as it all the way out to x, and the floor function gives us how many intervals. Remember that? So our j is going to start at 1, and it's going to end at that expression that we had with the floor function. Okay, we're going to go a couple minutes over. I hope that's okay. All right? So that's the sum of the delta y's for all the full intervals. Okay? And then the little bit more, okay? What goes into the rate? So what rate are we going to use for that last partial little interval?
X minus a over.
So where do we get that rate from? What x value do we get the rate from that will apply to that little part right there? Left of x. Okay? And how far do we go in that interval? X minus left of x. Right? Final x minus the left end will give us that little distance right there. That's our partial delta x times the rate at the left end. Okay, so don't zip and tune out. So here it is. This is our accumulation function that we've worked hard to build here and understand every bit and piece of it. Okay, but so like I said, you're responsible to understand where it comes from and what every expression means, not just plug things in and use it. Okay, you really got to know. So we have to know what's going on, not just be able to plug in numbers. Okay, so for your homework, I posted this along with your homework. Okay, and you're going to have to use Graphing Calculator, and to our file that we started, that I showed at the beginning of class, that we worked on last time, you're going to now add the accumulation function as a command line to that file. So that's what it'll look like as a command line. So to get the summation notation, it's going to be Control S. Okay, it's also a choice in the math menu. So Control S will bring up the summation notation. Okay? And give you blank spots to put your starting value and finished final value. Another thing we want to do in Graphing Calculator is show two graphs side by side, like I've been doing before. So putting a prime by the x and the y, what that tells Graphing Calculator to do is start a new graph over here, and every time you use y prime and x prime, it's going to be a second graph on the right. Some of you had calculus before, and this has a meaning in calculus. Okay? That's not the meaning for Graphing Calculator. What this is telling Graphing Calculator to do is graph a second graph on the right. So you have two graphs side by side. So this notation has nothing to do with calculus. It's just a way of telling graphing calculator, make that second graph. So that's what we want to do. We have the original rate graph and the step function on the left. And then we have the accumulation function. Now we're graphing this thing on the right. Okay, get started on your homework early. See you Friday.
For the time, do you just do Y and then apostrophe?
Apostrophe, yeah.
Okay.
It's just apostrophe.
Okay.
Yep.
And do we have a quiz and recitation?
Yes, we do.
Okay.
Yep. I'll put on the homework. I'll post what's on it in the homework.
Having surgery on Friday.
Hold on a second.
Yeah.